In this video, I'm going to describe and formally define pushdown automata. In particular, I'm going to describe non-deterministic pushdown automata. This is exactly the machine that recognizes context-free languages. A pushdown automaton is exactly as powerful as a context-free grammar, so they recognize exactly the same class of languages. Let's start informally by comparing a pushdown automaton to a finite state machine. By the way, the plural of automaton is automata. So we say one pushdown automaton, two pushdown automata. So this looks a lot like our finite state machine. You've got a finite state control here with multiple states and transitions between the states, and you've got an input string shown here at the bottom, and this machine will scan the input string character to character, never backing up. The real difference is that the pushdown automaton has a stack, and this stack can be pushed and popped during the execution of the so-called program for the pushdown automaton. So in addition to going from state to state, like a finite state machine can, as we read each character, the machine can also push and pop characters on the stack. And this stack serves as a form of memory. So the input string is the same as in the finite state machine. Namely, we read each character, and as we read the characters, we advance. And we have to read the entire string to accept or reject, and we can never back up. The stack has your typical stack operations. We can read the top of the stack and pop the stack. Those two operations are combined, so you read and pop at the same time. Or in a transition, you may choose to ignore the stack altogether. And you can also push something onto the stack, or if you don't need to, you can not push anything. We have an input alphabet, as before, characterized by sigma, but we also now have a stack alphabet, which is characterized as gamma. So this is the symbol for gamma, and gamma is a set of symbols, just like sigma is a set of symbols. They may be different, and typically they are somewhat different, but they need not be different. They can share symbols, or in fact they could be identical if you wanted. The state transitions in a finite state machine depend only on the state you're in and the current input symbol. In the pushdown automaton, the straight transitions also can depend on what's on the top of the stack. And in addition, each transition has the option of pushing something onto the stack. And finally, the machines that we're describing are going to be non-deterministic. It turns out that in the case of finite state machines, there is no difference in power between deterministic finite state machines and non-deterministic finite state machines. But the same is not true with pushdown automata. There's a difference in power. The non-deterministic machine is strictly more powerful than the deterministic pushdown automaton. When we get to Turing machines, we'll once again find out the situation is a bit more like the finite state machines. With Turing machines, non-determinism doesn't buy you anything. Deterministic and non-deterministic Turing machines have the same amount of power. But in the case of pushdown automata, the determinism or non-determinism is an important difference. When we say pushdown automaton, without any further explanation, we'll assume that it's a non-deterministic pushdown automaton. Okay, now let's look at the notation we're going to use for our pushdown automata. Above, we see a transition in a finite state machine. Each edge is labeled with a single character from the input alphabet. In the pushdown automaton, each transition is labeled with three things. The first is an input symbol. The second is the symbol on top of the stack, and that symbol gets popped when this transition is taken. And the last thing is a symbol that will get pushed onto the stack. When this transition is taken, something is popped off the top of the stack, and this transition can only be taken if the top of the stack matches the symbol here. And then once the transition is taken, we advance one symbol on the input and we push this symbol on the stack. Now, these can be empty. So the first symbol can be epsilon, in which case nothing in the input is scanned. In the case of B, the second symbol can be epsilon, and that means that the stack is neither to be read nor to be popped. So the transition can be taken regardless of what's on top of the stack. And in the last symbol, epsilon means that we do not push anything onto the stack when the transition is taken. So notice, with all these epsilons, we have non-determinism. So the machine is non-deterministic in general. Before we go any further, let's look at an example. Here's a language. The input alphabet is 0 and 1, and the language is all strings that begin with zeros and end with ones and have the same number of zeros as ones, possibly including, and the language includes the empty string as well. So we can see right away that our input alphabet consists of 0 and 1. In the pushdown automaton that we're about to design, gamma, our stack alphabet, has some overlap with the input alphabet. Gamma consists of two symbols, a $sign and a 0. We're going to use the $sign to watch for the bottom of the stack. Okay, we could use some other symbol, possibly even a 1, but the $sign seems to be the clearest thing to choose. And we could use another symbol here for 0, but it seems that 0 is probably the clearest. So here's our machine to recognize this. And let's look at how it works. Here's the starting state. In this case, we only have one final state. D is our accepting state. In general, we could have multiple accepting states. And we have transitions, and each transition is labeled the way we discussed. There are a lot of epsilons here. But basically how this thing works is the first transition is taken, we ignore the input. We ignore what's on the stack. As the machine begins, the stack will be empty, so there's nothing on the stack anyway. But what we do is we push a $sign. Then, in this transition, we scan zeros. So when the input is 0, we can take this transition. We ignore the stack. We don't look at what's on top of the stack, and we don't pop the stack. But we do push a 0. So every time we read a 0, we push a 0 onto the stack. Then, at some point, unfortunately we have non-determinism here, so we don't need to know exactly when to take this transition, we move over to state C. And this is a complete epsilon transition. We don't look at the input, we don't look at the stack, we don't push anything on the stack, we just move to this new state. And after we've made that transition, we scan ones. And for every 1 we scan, we read a 0 from the top of the stack. We look at the top of the stack, and if it's a 0, then we can scan a 1. So we're matching up the 1s in the second half of the input with the 0s that are on the stack. And we pop the 0 when we read it. We don't push anything, and so this makes sure that the number of 0s is the same as the number of 1s. And finally, when we reach the end of our 1s, we take this final transition, and at that point, the stack should be empty except for the $sign that we pushed at the beginning. And we pop it, and then we end in an accept state. Now remember, the definition of the pushdown automaton means that we can only accept the string if we scan the entire string. So we have to have read the last 1 before we take this transition in order for us to accept that string. So when is a string accepted? The machine begins execution in the start state, and it must end in an accepting state. Sometimes we call the accepting states the final states. In addition, it must consume all of the input symbols. It's okay to leave stuff on the top of the stack, so the machine can end with stuff on top of the stack. If we don't want to leave stuff on top of the stack, it's easy enough to add an extra state and a transition that scans everything off the stack. It's also easy enough to detect the bottom of the stack. We saw that in the previous example. We start by using a special symbol such as $. We begin the execution of the machine by pushing the $sign onto the stack. And then at the very end, right before we accept, we pop that $sign to make sure that the stack is empty. We can use that technique when we're creating push-down automata if we want to. And basically this is saying that there has to be a path through the finite state control that scans each one of the inputs and matches and takes transitions as it's supposed to. This is basically just saying if there is any path through the finite state control that scans all the input and treats the stack normally, that is, it doesn't make any mistakes with the stack, it only reads things that are at the top of the stack, and so on, and ends up in an accepting state, then that string will be accepted. There may be other pathways through the finite state control that don't end in an accept state. It is, after all, non-deterministic, but all there has to be is one pathway through the finite state machine to an accepting state in order for the string to be accepted. It's not possible to pop an empty stack. Okay? The second symbol, the B, which we refer to symbolically as B, but can also be an epsilon, means read a B and pop it. The top of the stack has to be a B, which means it can't be empty in order to take this transition. If there's an epsilon in this position, then it means we don't need to look at the stack, and we do not look at the stack. So it may or may not be an empty stack. We still can take the transition. And again, to repeat, this is a non-deterministic machine. We just have to find one pathway through the finite state control from the start state to the accept state in order for us to accept the string. So we have two conditions. The string has to be completely consumed, and we have to find a pathway through the finite state machine from start to accept that accepts that particular string. Here's the formal definition of a push-down automaton. It's a tuple with 6 elements, a 6-tuple, if you will. Q, sigma, gamma, delta, Q0, and F. So let's look at what we need to specify in order to specify a push-down automaton. We need a set of states. That's the set Q. We need an input alphabet. That's sigma. Then we need to say what kinds of symbols will go on to the stack, and that's the set gamma. Then we need a transition function, delta, and we need to identify a starting state. I'll come back to delta in a second. We need a starting state Q0, which should be one of the states, obviously. And finally, we need to say which states are the accepting states. So we can have 0 or more accepting states, a subset of Q. Obviously, we need to have one accepting state for the push-down automaton to recognize any language besides simply the empty string, because to recognize any strings at all, the empty language would be recognized by a push-down automaton that didn't have any accepting states. So now let's look at the transition function, but first let's use some notation here. We want to allow epsilons on the edges, so here we're going to say that sigma sub epsilon is just the set of input symbols and epsilon, and that's how we label the edges. Okay, that's the B in the previous slides. So the transition function requires a state, an input symbol, and a stack symbol, which is read and popped. And the input symbol can also be epsilon, and the stack symbol here can also be epsilon. So gamma sub epsilon is just the stack alphabet plus epsilon. So given a state and an input symbol and a symbol on top of the stack, we go to, and here is non-determinism, we see the power set. Okay, we go to a number of states, and for each one of those edges to a different state, we have the symbol that is pushed onto the stack, possibly epsilon to indicate nothing is pushed. Here's another example. We're going to talk about the language of palindromes. And we have a specification of what palindrome means, and then we have a context-free grammar, and then we have the push-down automaton that recognizes the language. A palindrome is any string that can be divided into first half and second half, and the second half is just the first half reversed. These are three examples over the alphabet of letters. Madam, I'm Adam. Okay, if you reverse it, it's Madam, I'm Adam. Was it a cat I saw? C is in the center. And this one I like the best. No lemon, no melon. Okay, reading backwards, no lemon, no melon. Okay, so we're interested in the set of palindromes over the alphabet 0 and 1. So the set of strings of 0 and 1, where the first half is equal to the second half reversed. Here is a context-free grammar for this. We have only one non-terminal S and 3 rules. For every 0, there's another 0 at the other end. For every 1, there's another 1 at the other end. And finally, there's epsilon. So this shows that this language is, in fact, a context-free language. Remember the definition of context-free language. If there is a context-free grammar for it, then it is a context-free language. Here's a grammar. So this is a context-free language. And also remember that if it's a context-free language, then there is a push-down automaton to recognize it. We'll prove that elsewhere. But for now, let's just look at the push-down automaton that recognizes this language. So again, we're using this trick of pushing a $sign onto the bottom of the stack so we can check for the stack being empty. And then we are checking here right before we take our final transition to make sure that there's a $sign at the top of the stack. And since we don't use dollar anywhere else, we know that the dollar that we're popping here must be the one we've pushed on the first transition. And so therefore we're at the bottom of the stack. So this is a very similar machine to our previous example. We stay in state B for a while, scanning 0s and 1s, and then we take a transition and we ignore the input, ignore the stack, and don't do anything to the stack. At some point, which would be the midpoint in the palindrome, and now let's look at these transitions. The transition here scans a 0. Whenever there's a 0 in the input, it pushes a 0. Whenever there's a 1, it pushes a 1. So you can see we're pushing our input onto the stack. And by the nature of stacks, when we pop it, it'll be in the reverse order. So this transition here is checking for 0s, and there better be a 0 at the top of the stack, in which case it is popped, and we don't push anything. So for every 0 on the stack, we scan a 0 and pop a 0. For every 1 at the top of the stack, we scan a 1 and pop it. One last thing to mention about this particular thing is I had an example palindrome here where it had a letter in the middle, I and C. And I wanted to note that this particular language only accepts or only includes strings that have an even number of letters, of 0s and 1s.